Hello, we're Team 7 studying Burj Arab. This week, every member did research and study about the exoskeleton and concentrated on their major roles. Since last presentation, our team began our study about the main building of Burj Arab. This week, we'll be looking into detailed parts of the main building. Let's get on with our 8th presentation. As usual, we'll start off with a quick review about the V-shaped core, then move on to this week's episode about the wind load and the solution. Lastly, we'll end our presentation with a short preview about next week's contents. Last week, we've learned the background of architect Tom Wright's decision on the V-shaped core to express the shape of a yacht and the characteristics and construction problems and solutions given to the building accordingly. The two characteristics of Burj Al Arab appear because of the V-shaped core. They are the fabric wall, which makes the sail-shaped hotel more realistic, and the huge 180 meters tall atrium. Using V-shaped core naturally formed a huge atrium between the core and fabric wall. As such, V-shaped core gave various characteristics to the building, making it more special, while also generating various problems. The utmost problem was about the direction of the building. Tom Wright wanted the building to face the shore, while the others wanted it to face the sea. According to client's decision and because of the wind problem, the Burj Al Arab was decided to face the shore. The reason for this decision is that Dubai, located in a hot place, has strong wind, and under these conditions, for tall buildings such as Burj Al Arab, the building's shape should be as wind-free as possible. Therefore, architect Tom Wright made the front to face towards shore in order to reduce the area of the building facing the strong wind of the sea and made the sharp part of the core to face the sea. Other than wind problem, they needed to build the main building in 3 years because of the too much time spent in building the artificial island. To solve this, the constructor used core structure advanced construction method, which is constructing the core in advance to lead the whole process. To safely apply this method, they used auto climbing system that uses hydraulic unit and rail to create concrete. Also, Burj Al Arab used total of 3 tower cranes consisting of 1 main crane and 2 sub-cranes. Main crane was placed higher than the other two because of the CSACM, and this week we will take a closer look at what role the main crane played in exoskeleton construction. In actual yachts, wind is an important factor that drives the yacht forward. However, such factor does not apply to buildings. For Burj Al Arab, wind was a problem. Various technologies and materials have developed resulting in the construction of high-rise buildings. Heavy weight may be the main problems when building a skyscraper, but the biggest problem is the wind. Wind loads are fatal to high-rise buildings because they become stronger with higher altitudes. With the development of reinforced concrete, the ability to resist wind loads has increased, but the complete solution has been difficult. Therefore, most skyscrapers have their own solutions to withstand this wind load. Burj Al Arab was no exception. Being a 321-meter tall skyscraper, structural engineer Anthony McCarter was also facing problems with wind loads. There are 3 main ways to solve the wind load of skyscrapers. The first is to narrow the floor plan as the shape of the building moves to higher floor, and the second is to reinforce the building using steel structures. The last is applying technologies to resist wind loads such as damper and TMD. The Burj Al Arab's form was already narrowed to higher floors, therefore they required additional steel structures. Therefore, during the design phase, structure engineers required designers to create steel structures. However, it was difficult to add a steel structure inside the Burj Al Arab, which already had its interior drawings completed. Consequently, the structure, to resist the wind load, was forced to go outside the building. However, there was a problem. The designer demanded that the exoskeleton be as thin and beautiful as possible so as not to disturb the exterior and bother the guests. So the structure engineer was in a situation where he had to complete the structure in a seemingly beautiful form while resisting the wind load completely. How did he solve this problem? There are two main structures that resist the wind load: exoskeleton and truss. This week, we'll learn about exoskeleton. Exoskeleton consists of two types of steel structures: main exoskeleton rear leg on the side and rear brace frame or X-span on the front. The main exoskeleton rear leg is composed of two legs and stretches up to 273 meters. The total weight of the rear leg is 2,800 tons and the weight of one segment is 40 tons. The X-span is total 3 in the whole building and it connects the two wings of the core together. Its weight is 1,600 tons total. There was three problems concerning the construction of rear leg. Firstly, it had to show a beautiful curved shape. Secondly, it was not supposed to be too thick because of the exterior the architect wanted. Simply put, it had to be thin, simple, curved beautifully while being able to resist wind loads properly. Lastly, as the building is located on sea, corrosion of steel can occur. Therefore, measures for this corrosion were also needed. How did they solve all these problems? To make the steel structure into a perfect curved shape, they were divided into 12 meters segments. The divided steel structures were able to effectively express curved shapes. However, the segments were still heavy, so the work was difficult. Because it was very difficult to adjust the angle to express the curve in the air, the two tower cranes were used to lift it up at required angle and connect the structure at the same time. The structural engineer constantly discussed the thickness of the steel structure with the designer. In order to withstand enough wind loads, a thick structure was inevitable. However, for designers, the client's requirement of beautiful exterior was also important. Therefore, the structural engineer designed the exoskeleton thin, which led to the installation of TMD, which we would learn later. Corrosion in steel structures is a very big problem. Serious levels of corrosion make the steel structure unable to function. Therefore, corrosion prevention was done by reinforcing the surface with steel plates treated by corrosion prevention spray. Solving the three problems discussed earlier, Burj Al Arab's rear leg construction began. Cranes that were already installed for the core construction were actively used for exoskeleton. The assembled segment were lifted and erected in position using the tower cranes from ground floor to top, one over another. When lifting, specially designed lifting lugs with 20-ton chain hoist were used to lift the segment in predetermined location and at required angle. Alignment of these segments was carried out using electronic digital total station located at three different fixed locations. The rear brace frame or the X-span's total length is around 60 meters. It was spliced into three pieces 24 meters, 12 meters, and 24 meters each. The first piece was lifted by tandem lift and erected between core embedment from one side, and the other end rested on the temporary girder. Once these two 24-meter braces were erected, then the X of 12-meter length of 52 tons was erected by two tower cranes as tandem lift. The last piece was lifted the same way. By lifting the horizontal frame, one X-span was done. This process was repeated 3 times to create total 3 X's in the building. By this, the exoskeleton of the Burj Al Arab is all installed. However, these exoskeletons could not completely resist the wind. Next time, we'll learn about truss, which is another way they use to resist the wind load, and how they attach the massive truss structures to the building. Thank you for listening.